All right, in this lesson, we're looking at solving exponential functions using common bases. All right, and the way this works, if we look at this property that we have here, this is pretty much self-explanatory. Really, the first example you could probably do on your own without me telling you anything. But if I have two things raised to a power, and those two things are the same, well, then the exponents have to be the same. So if I have a raised to the x equals a raised to the y, then x has to be the same as y. All right. So if I have the same base and they're both being raised to a power, the exponents have to be equal. If I have 2 to the 5th power, it's got to equal a 2 to the 5th power. It can't be 2 to the 6th power. All right. So if the base is the same, the exponents have to be equal. For example, if I look at the first one, I've got 3 to the x equals 3 to the 4th, and really common sense would tell us here that x would have to equal 4. All right. But in terms of the property, we're just looking at this. We're saying, okay, if the base is the same, if each of these are the 3, then the exponents have to be the same. The x has to be the same as the 4. In other words, x equals 4. We set up an equation. And it just so happens this equation is already solved for us. All right. If I look at the next one, it's pretty much the same thing. Saying, all right, if the base is the same, it's 4 raised to a power equals 4 raised to a power. If each of these has a base of 4, it means the exponents also have to be the same. In other words, the 2x plus 1 has to equal the 25. All right, so if the base is the same, the exponents have to be the same. And this one's a little bit more complicated because it's not already solved for us. But now from here, I have a pretty simple linear equation to solve. I subtract the 1 from each side. That gives me a 2x equals 24. And now I divide by the 2. So I find out that x equals 12. And that's it. All right, and I can plug this back in and check it and make sure it works. And I'll find out that it does. All right, but if the base is the same, then the exponents have to be the same. So I set them equal to each other and set up this equation. All right, if I look at the next one, here the bases are not the same, so what I have to do is I have to get the same base, all right? And when I do this, I'm just going to rewrite this so they have the same base. So when we look at a 4 and we look at a 16, we should notice that these things have a relationship, that 4 and 16 are related in some way, that 16 is actually 4 squared. So right there is your common base. When you look at this, right here, 4 to the 8x, that's fine the way it is. But right here, 16 to the x plus 6. Well, 16 we know is 4 to the 2nd power. So I just rewrite it as 4 to the 2nd power. And notice I haven't changed anything here. I've changed the appearance, but I haven't changed the values of anything, all right? I haven't done anything to each side of this equation. I just rewrote the 16 in a different format as 4 to the 2nd power, all right? And now from here, rules of exponents, the 4 to the 8x, that stays exactly the way it is. But now right here, rules of exponents, when I've raised something to a power like I'm doing here, I multiply the exponents. So this ends up giving me a 4 to the 2x plus 12. I do the 2 times the x plus 6, and when I do that, I distribute. Now I have the same base, so now I can say that these exponents are equal to one another, so the 8x equals the 2x plus 12. And now from here, I just solve for x. I'm going to subtract the 2x from each side. So I find out that 6x equals 12. I divide each side by the 6, and I find out that x equals 2. And that's it. All right. So again, I'm going to rewrite this so they have the same base. So I'm looking for a common base. Once I have them rewritten, if the base is the same, I can set the exponents equal to one another. Same thing with the next one. When I look at the 9 and the 27, I start to think about what number I can rewrite each of these as. So I want something raised to a power that equals 9, and then that same thing raised to a power that equals 27. And the common base here, the number I come up with, is a 3. 9 is the same thing as 3 squared. So I have 3 squared raised to the 4x minus 2. Over here, 27 is the same as 3 to the 3rd. So I have 3 to the 3rd raised to the 2x minus 8. And now back to my rules of exponents. When I raise something to a power, I multiply the exponents. So this is going to become a 3 to the 8x minus 4 when I distribute. This next one is going to become a 3 to the 6x minus 24 when I distribute. And now from here, I have common bases, so I can set the exponents equal to one another. So that means the 8x minus 4 equals the 6x minus 24. All right. And now from here, it's just solving a linear equation. I'm going to subtract the 6x from each side. That gives me a 2x minus 4 equals a negative 24. I'm going to add the 4 to each side. Let me rewrite that guy up here. That's going to be a 2x equals a negative 20. And now I just have to divide each side by the 2. Okay. And that's it. And when you look back at these, really there's more than one common base that I could go with here. With this particular example, the 9 and the 27, 3 is the only viable option. If I tried using something like a 9, that'd be tough because 9 to the 3 halves power is the only thing that would give me a 27. Something like this first example, this one 2 would have also been a viable option. I could have done 2 to the 2nd power. This one I could have done 2 to the 4th power. And really, it doesn't matter if I choose the 4 or the 2 in this example. It's going to give me the same answer either way. Here I get a 16x as the exponent. Here I get a 4x and a plus 24. But you can see the end result is going to be the same if I solve this without showing much work. Okay, so keep in mind, you can use any base you want as long as you get a common base. All right. If I look at the next one, this is where it becomes a little bit tricky when I look at fractions, okay? If you see a fraction, essentially what I want you to do is ignore the fraction itself, just look at the denominator. So here, if I just look at the denominator, if I just compare the 2 and the 4, the common base between 2 and 4 is 2, all right? So I'm going to rewrite each of these in terms of a 2. So this one I'm going to do 2 raised to a power. Again, ignoring the fraction, just looking at the denominator, 2 to what power just gives me this denominator, just gives me the 2. It's 2 to the 1st power, all right? So if I want a fraction, instead of 2 to the 1st power, I do 2 to the negative 1st power. Because remember, that's what negative exponents do. They create fractions. They cause us to flip to the other side of the fraction bar. So again, when you look at this, look at the denominator, say 2 to the 1st power is 2, so 2 to the negative 1st is 1 over 2. All right? And then that's all raised to the x power. Over here, I have 2 to the 2nd power, which is an x minus 9. Sorry, raised to the x minus 9. And now I multiply the exponents, so that gives me a 2 to the negative x equals 2 to the 2x minus 18. Now I have a common base. I set the exponents equal to one another, and I go ahead and solve. So in this one, I'm going to go ahead and subtract the 2x from each side. It's going to give me a negative 3x equals a negative 18. And now from here, I just have to divide by the negative 3. So I find out that x equals a positive 6. Okay? So again, if I look at the next one, here, I could use a common base of 9. I'm going to use a common base of 3 just to show you how these fractions work a little bit better. 9 is probably the better option, but we're going to use a 3 just to show you how this works. So again, when I look at these, when I look at the 9 versus the 81, so I think about maybe the number 3. Well, 9 is 3 to the 2nd power. So if I want 1 over 9, I do 3 to the negative 2nd power, and that's it. Okay, so that's how the fractions work in terms of trying to get a common base. Just look at the denominator and then write it as a negative exponent instead. Okay, again, I could have done 9 to the negative 1st and then over on the other side 9 to the 2nd, but I'm doing the 3 just to show you it works out just fine. So that's going to be 3 to the 4th power. And now from here I multiply the exponents. Now the bases are the same, I set the exponents equal to one another. And then from here I'm going to solve. I'm going to subtract the 4x from each side. That's going to leave me with a negative 6x equals 16. I'm going to divide each side by the negative 6. And when I reduce that fraction, that's going to be an x equals, that's going to be a negative 16 over 6, which reduces to a negative 8/3. Okay, and if you chose a common base of 9, you'll get the same thing. All right. So again, when we do this, we don't do anything to each side of the equation. We just rewrite the number so that each one has a common base, that it's the same number raised to a power. Once I have that, I set the exponents equal to one another, and I solve. Okay.